Hello, class, and happy Wednesday. Welcome to our class, and we're going to start this one with a quick question. How could you tell a towel is dry scientifically? So I know it feels dry, but how would you know that it is completely dry or all the water's gone? Just take a second and think about that. Now, the best answer I'm going to give you is by weighing. And we're going to use this method a lot this year in a lab setting. And you're also going to see plenty of questions this year where you need to answer the question, is the substance completely dry? Now, how can I use weight to determine that it's completely dry? I weigh it, I heat it, I weigh it, I heat it until it stops losing mass. Because the process of heating it is drying it. That water is evaporating. So as you have a wet towel and you heat it up, and then I weigh it, that wet towel should be losing mass as you're heating it because it is drying. That water is leaving the towel and evaporating. We're going to use that same process in today's lesson, looking at thermal decomposition. We're going to be looking at worksheet 1.9, which you have in your learning packet. You also have access to right here. Okay? So on worksheet 1.9, the front is going to be done in class. I'm going to teach you how to do that today. And the back is for your homework for you to do. They're very similar questions, okay, almost identical, just the compounds and the numbers have been switched around. I'm going to teach you how to do it, and then I want you to do it on your own. And this is called a thermal decomposition type of problem, where we're analyzing lab data and drawing conclusions based on the data. And this is going to be a lot about what the AP exam looks like. You're given a set of data, and you're asked questions dealing with that data. Okay? Today's homework, 1.9. Do it when you can. I want the goal for us is to be done with worksheets 1.1 through 1.9 by Friday. So by Friday at midnight, I want you to have turned in the worksheets 1.1 through 1.9 via Schoology. And the link to do that, you can find it in Friday's folder. So you should hit submit there when you're done with all of those worksheets. And our goal is by Friday. So after that, you're starting to work on the review, and I'll have kind of a practice quiz for you to do as well. Virtual students tomorrow, please check Schoology in the morning. I'm going to kind of make my plan tomorrow, which is Wednesday for me, during the day, and I'll post directions on what you should be doing on Thursday, sometime on Wednesday or Thursday morning. So virtual students on Thursday, please check Schoology Wednesday night or Thursday morning just to see if you have to Zoom in or not. Again, plans are very fluid here, so I'll try to keep you up to date the best that I can with what to expect. In-person students, Thursday, expect to complete a lab. Virtual students, you'll probably have some work time and some other activity, which I will describe for you in Thursday's folder. I'll either finish that Wednesday sometime or Thursday morning. Okay? All right, today's lesson, we're going to go through the front of 1.9. So I ask you a few questions based on this data. I'm going to kind of walk you through my thought process as I'm analyzing this data. So, in the first of two experiments, a student is assigned the task of determining the number of moles in one hydrated compound of magnesium chloride. So what happens here is you can buy hydrated compounds which have molecular water attached to it. And it looks like this, okay, the formula. Instead of an N here, there's typically a number. It might be 5, it might be 6, it might be 2, it might be 3, whatever. It can be anything. And at the molecular level, water has been attached to it. It's hydrated. So what you can do is you can heat it up and that water is going to evaporate, the substance is going to become lighter. What we're doing in this experiment is we start with a hydrated form of magnesium chloride, which has, again, water attached to it. I heat it up. It loses mass. From that mass, I can determine the ratio of magnesium chloride to water. So this is kind of a blend. This is an empirical formula problem, in a way, and it's also a decomposition problem, because I'm looking at how much mass is lost and calculating how many moles that would be. All right, so I start with an empty container. I put the sample of magnesium chloride in that container, and it weighs 25.825. Then I heat it up. I weigh it. It weighs 24.982. I heat it up some more. It weighs 23.976. I heat it up. I weigh it some more. It weighs 23.977. Explain why the student can correctly conclude that the hydrate was heated a sufficient number of times in the experiment. So this goes back to our initial question. How do I know a towel is dry? Well, I can weigh it, heat it, weigh it, heat it, weigh it, heat it. What's eventually going to happen? It's going to stop losing mass. Once it stops losing mass, all of the water has evaporated. Therefore, the substance is dry. Has this substance stopped losing mass? Yes, it looks like it even gained 100th. We can ignore once you get to that level of degree, okay, or 1,000th, and it's basically the same. 0.97, basically the same. It has stopped losing mass. So this is called weighing to constant mass, and you're going to see this used throughout the year. How do I know a substance is dry? The constant mass indicates the removal of all water. So try to use that key term, weighing to constant mass. Therefore, all of the water is gone. The constant mass indicates the removal of all water. The hydrate is now anhydrous salt, meaning there's no water in it. Okay, so I don't mean to confuse you with these terms here. The hydrate means there was water attached to it. Anhydrous means the water, there is no water. Okay? Okay. All right. Number or letter B. Using the data above, calculate the total number of moles of water lost when the sample was heated. So I started with 25.825. I ended with 23.977. What did I lose in that process? I'm losing water. That's why I'm heating it. It's losing water. So I can figure out the mass that I lost there, and what that mass is water. The question asks me to calculate the number of moles of water. Well, I just calculated mass of water. Can I turn that to moles? Yes, using the molar mass, using molar conversions, which we've been using. Okay, I know I'm a little more precise here. If you just use 18.02, that is perfectly fine. Okay, so I take 1.848 divided by 18.02, and I get 0.1026 moles of water. That is the amount of water that was lost in this process. Now we're going to use that to figure out the formula. How many moles of water are there compared to 1 mole of magnesium chloride? So that was letter B. Letter I. Let's look at II. Determine the formula. Well, remember, what is a formula? A formula is a mole ratio. If I look at something like H2O, there's 2 moles of hydrogen for every 1 mole of oxygen. I want to figure out the formula ratio here. So we're not looking at exactly like a formula of how many hydrogens to oxygens. We're looking at how many moles of water are there compared to how many moles of magnesium chloride. So to do this, I need to also figure out how many moles of magnesium chloride I have. Well, after I've lost all the water, what should I have? I should just have magnesium chloride. So this mass right here is my mass of magnesium chloride, but keep in mind, I also have a container. So I do need to subtract that mass of the container, and that gives me my mass of magnesium chloride. Once I have my mass of magnesium chloride, I can convert that to moles using my molar mass. So now I have a mole ratio. In letter I calculated how many moles of water there were in my sample. In letter I calculated how many moles of magnesium chloride there are in my sample. To figure out the smallest whole number ratio, remember, I want to divide by the smallest number. We're going back to empirical formulas. So I compare moles of water to moles of magnesium chloride. It looks like moles of magnesium chloride is a much smaller number. So I divide both values by the smallest number. Moles of water divided by moles of magnesium chloride, and moles of magnesium chloride divided by itself. This obviously is going to be 1. This ends up being a whole number, 6. So what is my ratio of water to magnesium chloride? 6 to 1. So how would I write that hydrate formula? Well, typically I write the formula for magnesium chloride, a dot separating it, indicated it's connected through a hydrate, and then I have 6 waters attached to this magnesium chloride. So for every 1 magnesium chloride, there are 6 waters attached to it. And we'll study hydrates more so later on in the year, but for now, let's just focus on, can you get the formula of a hydrate given some data? All right, hopefully it makes sense. If you have any questions, again, remember, shoot me an email. We can always Zoom tomorrow, or ask me in class, or we can find a time so that you can understand worksheet 1.9 correctly to turn in by Friday. Determine the molar mass of the hydrate. Hopefully we can finish this up just by looking at the formula. How do I get the molar mass of a formula? I add up magnesium and chlorine or whatever elements are in my compound. So in this case, I need to get the formula or get the molar mass of magnesium chloride and the molar mass of water, but I need to take into account there are 6 waters. So whatever water's molar mass is, I'm multiplying by 6. So here's the molar mass of magnesium chloride. Here's the molar mass of water. Again, I'm multiplying water by 6 because there are 6 in my hydrate, and I get 203.303 grams per mole is my proper unit for molar mass. Okay, so hopefully that allows you to do a very similar problem on the back, dealing with some other compounds. Another type of problem we'll see is precipitate. And I'm just trying to give you a variety of questions, and we're going to look at a variety of questions all year where we're looking at experiment data. We'll also do plenty of experiments on our own where we analyze our own data, but the more data and the more problem solving you can do, the better off you'll be taking that AP exam or just understanding chemistry in general. It's really a problem solving science where we need to look at data and understand what conclusions can I draw. So let's look at our next problem, where we look at a mixture forming a precipitate. So I have a mixture, okay, in a jar, anywhere. It contains sodium chloride and aluminum sulfate. A 1.45 gram sample of my mixture is dissolved in water. To create a precipitate, I add sodium hydroxide. What does this produce? Aluminum hydroxide. The precipitate, the solid, is filtered, dried, and weighed. The mass of the precipitate is 0.01 or is 0.107. What is the mass percent of each component in the sample? All right, so here I have a chemical reaction because I had a precipitate form from substances dissolved in water. Now, what we need to focus on is what is the chemical reaction that occurred. So it looks like I added sodium hydroxide to my mixture and it produced aluminum hydroxide. So what I want you to first ask is which of my substances that was in the mixture reacted. Did sodium chloride take any part in producing aluminum hydroxide? The answer? No. There's no sodium, there's no chlorine. Sodium chloride didn't do anything, so I can ignore it for now. But aluminum appears to have. Aluminum must have reacted with hydroxide to produce this new compound, aluminum hydroxide. So, what I'm going to do is I'm going to write a chemical reaction describing what happened in my reaction. Aluminum sulfate reacts with sodium hydroxide, produces aluminum hydroxide. Now, what other substance would there be? Well, it must be sodium sulfate. And where did I get this Na2SO4? The process of elimination. I know aluminum sulfate must have reacted with sodium hydroxide, okay, to produce this aluminum hydroxide. So there's my product. Well, what else is left? Because remember, nothing can appear or disappear. There's both sodium and sulfate. So I just wrote my formula for sodium sulfate as my other product. Okay? Now, this is called a double replacement reaction, and we'll study it in further detail later on. For now, hopefully you at least get the basics of how I wrote that chemical equation. With every chemical equation, please balance. I have 2 aluminums, 1 aluminum, I'm going to add a 2. I have 3 sulfates, 1 sulfate, I add a 3. I have 6 sodiums here, I need to add a 6, and that actually balances my hydroxide. So this is my balanced chemical equation. All right, so the precipitate, what is it? Well, the precipitate is aluminum hydroxide, okay? So that can be a starting point to figure out how much aluminum sulfate I must have started with. Because I added an excess of sodium hydroxide, aluminum sulfate must be my limiting reactant. So I want to figure out how much aluminum sulfate was in my mixture based on how much aluminum hydroxide I produced. Okay? So what I'm doing here is I'm creating a precipitate. I'm drying that precipitate, I'm weighing that precipitate, and I'm using it to calculate how much reactant I started with based on the amount of product produced. Okay? Now you can do that for the limiting reactant of the reactant. Okay? Which one you know you're completely out of. Okay? All right, so in this case, aluminum hydroxide was produced from aluminum sulfate. That is my limiting reactant. I want to see how much aluminum sulfate I must have had to produce this amount of aluminum hydroxide. I'm just doing stoichiometry, going from aluminum hydroxide to aluminum sulfate. So I go to moles of aluminum hydroxide, I go to moles of aluminum sulfate, and then I go to grams of aluminum sulfate. Now, once I get grams of aluminum sulfate, this tells me how much aluminum sulfate I started with. That was in my mixture. Well, what was my mixture? Again, it started as 1.45 grams. Well, I know that in it there must have been 0.235 grams of aluminum sulfate, which was completely used up to produce this precipitate. So what part was sodium chloride? Well, I would just subtract. The total was 1.45. I know there were, of that 1.45, 0.235 grams was sodium chloride. This is my mass of sodium chloride in the mixture. This is my mass of aluminum sulfate in the mixture. To get mass percent, I just need to figure out what the percent of each compound was in the mixture. So I take the individual amount divided by the total. So the percent of aluminum sulfide would be the individual amount, 0.235 divided by the total, times 100. There's my percent of aluminum sulfide in the mixture. You could take 100 minus that, or do the same math. 1.22 grams of sodium chloride divided by 1.45 times 100, and there's my percent of sodium chloride in the mixture. These are my mass percents of each compound in the mixture. A trickier problem, but hopefully you can get it on your own on the back of 1.9. All right. So today's goal was to understand how to analyze lab data, especially looking at weighing to constant mass, taking that mass of my product produced and using it to solve other things, using it to solve how much reactants we had or how many moles of water was in the hydrate. Other things I would like you to do for tomorrow if you're in person, or for Monday if you're virtual, okay, but going to be in person on Monday. Please read through the lab that I've attached to the Schoology site. Read through it. The more familiar you are with what we're doing, the quicker we can get through it, the more smoothly it should go. So please read through it, look through it, and come with questions if you have any. I look forward to seeing you in person on Thursday, possibly in person Monday. If you're virtual, keep an eye on Schoology. I'll be giving you directions daily on what you should be doing daily, and giving you times to check in. If you have any questions, please shoot me an email. We can meet over Zoom and answer those. Happy Wednesday. Happy studying. Good luck with your homework. Work on finishing 1.1 through 1.9 for Friday.